So we've been talking a lot about how to draw molecules. Now we're going to start looking at how molecules actually behave. And what we're really looking at is how the electrons around the atoms in our molecules are behaving. That ultimately seems to control the chemical properties. So let's get into it. So the focus of today is going to be a discussion of electronegativity. Electronegativity is a long word, but it's an important word. I'm just going to abbreviate it as EN for electronegativity for the purposes of this lecture. So let's just recall a few things. Electrons in a covalent bond are shared. So that word shared is very important as we understand or try to understand the chemical properties of molecules. So electrons in a covalent bond are shared. A really important question is how do electrons actually get shared? And we looked at that a little bit. When we were talking about orbitals. So orbitals, again, are these the space volume that electrons can exist in. And so what we see is that electrons get shared when we have overlap of atomic orbitals. And it's worth just mentioning because it's so important that orbitals are the space, and because it's in 3 dimensions, that means the volume that electrons can exist in. Okay, so let's look at this in more detail. Let's say we have 2 hydrogen atoms, and we let them sort of react with each other to, instead of being 2 hydrogen atoms, we have molecular hydrogen, or H2. Okay, so what we've done is we've mixed these 2 hydrogens together. They're called free radicals because they have a single unpaired electron that's not part of a lone pair. Anyway, we're going to do a chemical reaction and allow these things to form a covalent bond. So this is an example of a chemical reaction. A chemical property of the hydrogen atom is that when it's nearby another hydrogen atom, they engage each other to form a covalent bond. Okay, so once again, we have these electrons around the free hydrogen atoms before they do a reaction. And these electrons, shown as dots, when we show them as dots, it's kind of a simplification of what's going on. These electrons are residing, or they exist, in the 1s orbitals. So another way to picture this would be, we could have, instead of H dot by itself, we could draw H dot with a circle coming into close contact with H dot, and that's another circle. Let's imagine these 2 atoms are the same size and the circles were drawn uniformly, which I did not achieve. Anyway, okay, so we have these 2 H dots now sitting inside circles. The circles are supposed to be the 1s orbitals. You'll recall that the s orbital is a sphere drawn in 2D as a circle. Okay, and so when we want to think about where the electron, the single electron in the hydrogen atom is existing, it's just sitting in the s orbital in the first shell, because that's the lowest energy orbital, closest to the nucleus, easiest for the single electron to reside in. Okay, now let's once again do our chemical reaction where we put these things in close proximity with each other and we form a covalent bond. When we do that, we're going to see an H come in close contact so that we get overlap of our 2 circles, which again are spheres. Now, one way of kind of showing what's happening to the electrons, this is a way, it's not the way, it's not even a correct way, is to show the little dots in sort of the Venn diagram, if you've seen that before, just where the circles overlap. So the electrons are simultaneously existing in both orbitals. So the electrons simultaneously exist in both orbitals. That is to say, the electrons are shared. The electrons exist in both orbitals, the electrons are shared. So that's sort of shown nicely by having this overlapping region of the two 1s orbital spheres. There's that little part where they overlap. And so if an electron is in that little part where they overlap, the electron could be said to be in both orbitals at the same time. It turns out that's a little lacking. Quantum mechanics says quantum mechanics, this complicated field of mathematics and physics that really governs all the chemistry that we see, quantum mechanics says the electrons exist over the entire volume of both orbitals simultaneously. So both orbitals simultaneously. Now what that means is that when I draw the picture and I've got this one space where the orbitals overlap and I say that's where the electrons are, and you're like, oh, the electrons are in that overlapping place, so they're in both orbitals. The electrons are shared between the two nuclei. That's a really clear picture. It's actually an incorrect picture. Quantum mechanics, and we've proven this, and it's a really important thing, says that it's in both orbitals. It's actually in the entire region. So it's not just in this space between the two orbitals. It's in the entire space, I guess shown like that. The space between the two orbitals, the left orbital and the right orbital. Well, how can that be? How can you put the electrons over in this orbital and say that they're also over that orbital and that they're truly being shared? If they're in the green orbital, shouldn't they just be part of the green atom? Okay, let's look at that in a little bit better of a depiction, and that's called the molecular orbital. Molecular orbital. So far, we've looked at atomic orbitals, these orbitals that exist for electrons to reside in when atoms are by themselves. When you start mixing atoms together and form covalent bonds, then you start forming things called molecules. They're no longer, you wouldn't say water is an atom of water, you would say a molecule of water, a collection of atoms that are all bonded by covalent bonds. But we won't worry too much about that definition of the word molecule versus atom. Just, when have you ever said an atom of water? Well, if you have said it, I guess it was incorrect. Sorry, don't mean to be so hard. Anyway, so molecular orbitals. These are, back to the topic at hand, jeepers. These are orbitals that hold shared electrons and define covalent bonds. This is a bit of a lazy definition, but it's an important piece of what a molecular orbital is captured by this definition. That is to say, when you have a covalent bond and the electrons are shared between two atoms, the electrons no longer exist in atomic orbitals, they now exist in molecular orbitals. So as soon as you form molecules, you have molecular orbitals. Now, what's a little bit fishy about that definition is it turns out that what happens to lone pairs? Like if you have an electron that's not shared between two atoms, it's just by one atom, like the lone pair of the oxygen in water. Well, both of the lone pairs are also existing in molecular orbitals because the whole thing is now a molecule. It's no longer in an atomic orbital. We'll see that in future lectures when we get into something called orbital hybridization. But for now, suffice it to say, what we're going to do is we're going to take an atomic orbital on the atom of hydrogen, we're going to mix those together to form a molecule of hydrogen. So these are atoms, atomic orbital. Those circles are 1s atomic orbitals. What we're going to do is allow the electrons to be shared and allow the two 1s orbitals to form molecular orbitals. And I'll leave all, it's technically plural, there's two, but let's just worry about the one for now. So I'm going to be careful. Molecular orbitals form. Turns out that there's one molecular orbital for each atomic orbital that goes in, but that's too quantum mechanic-y for now. The idea is we're going to take these two atomic orbitals, and for the electrons to be shared, the atomic orbitals sort of merge together to form a longer oval. So I've got my oval shown here that results from two sort of circles. You could even see the circles a little bit, like circle here and a circle here. There's an overlap region, but now the whole thing reforms into a single molecular orbital to hold the electrons. Now, as I said, we actually formed two, but the second one doesn't get filled, so let's not worry about it right now. Now, this is important because now we're consistent with quantum mechanics. Start over. Electrons can exist anywhere inside the molecular orbital. And honestly, they do reside anywhere inside the molecular orbital. So that is to say, they're kind of everywhere in there. And that's something called the Heisenberg uncertainty principle. I'm getting too bogged down by the quantum mechanics. Let's keep going. So electrons can exist anywhere inside the molecular orbital. And both H nuclei, kind of the heart of the atom, exist in the molecular orbital. That means the atoms, excuse me, let's phrase it this way. The electrons are shared then between the two nuclei. It's sort of like the two nuclei decided to like move in. They were each in their separate apartments, separate orbitals with their electrons, and they moved in together to share a bigger space, a big molecular orbital. And now the two electrons came along for the ride. They're also in the bigger molecular orbital. Now, since the two hydrogens are living together, they have to share their electrons. Hopefully that's somewhat of a helpful analogy. Okay, so far we've just been talking about molecular orbitals. We haven't even touched on electronegativity. But understanding how things get shared is important to understanding how molecular orbitals form is important to understanding something called molecular orbital distortion. So let's get back to the term electronegativity. And that was again this En, and molecular orbital distortion. Okay. So what happens here is that in molecular orbital distortion, we see that the molecular orbital will be distorted when two different elements bond. So here's the key thing: when two different elements bond. Now let's look at a picture of what I mean. Hopefully the picture and the discussion of molecular orbitals will help us. Let's say we have H and H. Now when they bond, I need to be extra careful here. When they bond, they are going to form a fairly regular oval. A better artist would make this more even. Imagine a symmetric oval that could be shown in 3 dimensions as sort of the two spheres have kind of merged with each other. Now, with when hydrogen bonds to a different element like fluorine, something strange will happen. Despite the size of the atom and the number of orbitals that it has, we will see the bonding molecular orbital take on a different shape. We will see kind of a large region around, in this case, the F atom, the fluorine atom, and we have a smaller region around the hydrogen. So let's capture some of this. What we have when we have the two hydrogens bonding with each other, I wanted to capture that we have the same atom, which was H. Hence, we have no distortion. Now, when we have H bonded to F, we have two different atoms, which means we're going to have high distortion. And I guess the degree of distortion will vary based on which of the two elements we put in, using that property called electronegativity. The important thing is that with two different elements, different color here, we're going to see some distortion at least. Whereas if we have the same elements, as in the case of hydrogen and hydrogen, we won't see any distortion in that molecular orbital. Now, what does it mean to be distorted? So when an orbital is distorted, there's sort of a larger region and smaller region, because we're always talking about the connection of two elements. It's never more than that. I mean, it can be. Yes, it can be. In this case, in this class, we're going to focus on connections, covalent bonds between two atoms. And so we're, for the most part, only going to see this sort of thing happen when we have a distortion. That is, we're going to have a larger portion or a larger region. We're going to have a smaller portion. Is such a weird word. Let's change that to region. Sorry to make you erase. Okay. When we have a larger region in an orbital, that creates more space for the electrons to exist in. So electrons are more likely to exist in the larger region. And conversely, electrons are less likely to exist. Larger region, more likely. Smaller region, electrons are less likely to exist in the smaller region. Now that's just kind of thinking through, electrons exist in orbitals, these spaces or volumes. And so if we make one part of them larger or smaller, then we will kind of encourage electrons to be there or not be there in those respective spaces. Okay? So what this means is that when orbitals are distorted, the electrons are not evenly shared. When the orbitals are distorted, electrons are not evenly shared. Now, the biggest culprit of this is HF, which is hydrofluoric acid. It's a really interesting molecule. It can chew through bones because it sequesters calcium. So it can actually melt bones. It's incredibly toxic, but the poison aspect of it, toxicity meaning poison, the poison aspect of it's the least of your worries. If you're exposed to it, it will burn, and it's a weak acid, so it doesn't sort of burn and be done. It kind of burns and burns and burns and kind of can sort of regenerate its ability to burn. And as I said, it can chew through bones. There's this incredible scene in Breaking Bad, very powerful, where they wanted to decompose a body. Sorry, a little gross. So they use hydrofluoric acid. Unfortunately, we learned another chemistry lesson, and that is that porcelain and ceramic is also chewed up by hydrofluoric acid. So they should have put the body into a rubber container to preserve it. Anyway, or not preserve it, the opposite of preserving it. Sorry, tangent. Let's get back to business. So Hydrofluoric acid, we could show it as this line being a covalent bond, but the more precise way to draw it would be this distorted orbital that shows how the electrons are shared, and the electrons are more likely, it's two words, but more likely to exist. Oh, okay, whatever. To exist over F. Okay, so why is that? That has to do with electronegativity. So electronegativity what it describes is, this describes an atom's ability to distort the molecular orbital in a covalent bond. So there's the definition of electronegativity. So this is a property of an atom and describes how well that atom can distort a covalent bond. When an atom is more electronegative, the atom will cause the orbital to become larger over its nucleus. So if an atom is more electronegative, it will cause the molecular orbital to become larger over its nucleus. And vice versa for less electronegative. So the atom will cause the molecular orbital to be smaller over its nucleus. Less electronegative is smaller. So let's use this trend. We have H and F, which has the greater En. Or let's say it this way. This is a better way to phrase this. We have these two atoms, H and F, which is more / less electronegative. I'll give you a second to think through that, answer that. I'll provide an answer in just a second. So here's me stalling so that you can pause, so that you can pause, so that you can pause. Okay. I believe you've had the chance to pause, so now I'm going to label this one as the H as being more electronegative. Excuse me, the F being more electronegative, the H being less electronegative. I said that wrong, I wrote it right though. Okay, so based on the distortion, we see a larger lobe or a larger region over the F, suggesting that it's more electronegative than the hydrogen, which has a smaller region. Now that's generally true, so what you should know and this gets like stars and highlights once I actually write the trend, is that for us, H is approximately the same electronegativity as carbon. Nitrogen is more electronegative than carbon, oxygen is more electronegative than nitrogen, and fluorine is more electronegative than oxygen. And so this turns out to be the most electronegative element on the periodic table. And in general, group 7 is all much more electronegative than the other elements. Now, some of you have taken high school chemistry and have said, you know what, I could do one better. I'm going to go into the next page. Some of you will note that the general trend is this. What I wrote on the last page of your notes is the thing you need to know from me. And it's the thing that's because it's the most helpful for this class, not because I'm all-knowing and different than the rest of the chemistry community. This is just what's most helpful in this class. So here's the general trend, though, that many people have seen. Let's imagine I draw the periodic table. That looks pretty good. Okay, so this is a periodic table. The periodic table has periodic trends, that is, things that you can sort of predict without knowing anything about the, without knowing much more about the chemistry of the individual elements. What I'm going to first do, sort of cross off the noble elements. These don't count in this trend. But after that, generally what you see is that you go from increasing, you have increasing electronegativity as you go up into the right. So as you go up into the right, you generally see more electronegative elements. Here's the issue. I had that trend on the previous page. H is approximately equal to C. It turns out that H is way over here, and C is sort of in here. Now, C, which is less than N, which is less than O, that makes sense because they kind of go in series. It goes C, then N, then O, going to the right across the periodic table, and then F. So here, this makes sense to have an increase in electronegativity because we're just going across to the right to the periodic table. It's a little weird. You're like, okay, it doesn't really fit with H being approximately equal to C, but it's true. Now, the other issue is that we also have O, which is the same. O is actually less than Cl, Er, or I, which are all stacked on top of each other underneath fluorine. So the problem I'm trying to illustrate to you is that up and to the right doesn't always work. Instead, what you want to do is go back to here. So this is more electronegative. That's the trend I want you to focus on. Okay, that'll do it for this video. So I'm going to stop sharing. So in the next video, we'll look at the chemical effects of having differences in electronegativity, molecular orbital distortion, all of that in something that's called polarity.